6.6 log scales. The types of different log scales we're going to be dealing with are the Richter scale, the pH scale, and the decibel scale. Those are the most common that we deal with. And then we solve exponential equations algebraically using logs. These aren't actual log scales, they're just equations. But we have to solve them with logs because they have different bases. So we have growth and decay again, and then we have some electrical current type stuff. And we have base E coming back to us. All right, the Richter scale, you guys had to read through those. There's our Richter scale. Let's take a look at what it actually means. So we take a look at our Richter scale. An earthquake, it says on A, of a magnitude 8 is blank times as intense as an earthquake of magnitude 7. But the first thing you're going to do is you're always going to set it up in terms of 10 exponent something. Okay? So on letter A, you're going to go 10 exponent. You have one that's an 8, and you have 10 exponent one that's a 7. So all you're doing is you're taking 8 subtract 7 for your exponents. Okay, it's this simple, seriously. So you're going to take 10, 8 subtract 7 gives you 1. So it's 10 to the 1 times bigger. So it's 10 times bigger. Okay, and when you read through that first section, we know that each point on our Richter scale, so from 7 to 8, 8 to 9, each one of those increases by 10-fold. Okay, so it does grow exponentially. So let's see here. It's an earthquake of magnitude 7 is how many times as intense? As intense means as strong or stronger than an earthquake of magnitude 3. So on that one, all we're doing is 10, 7 subtract 3. What do we get? 10 exponent 4, which gives us 1 and 4 zeros. So 10,000 times as intense. Okay, so it's 10,000 times as intense. Okay, we're just solving 10 exponent 4. That's 4 zeros. Letter C, an earthquake of magnitude 4 is how much is intense. So is it stronger or weaker as an earthquake of magnitude 6? What do you think? It's weaker, right? So let's find out how much. So we've got 10, 4 subtract 6 gives us 10 to the negative 2. Now we're not going to write 10 to the negative 2. We're going to flip it. So that's going to be 1 over 10 squared. And what's 1 over 10 squared? 1 over 100. So it's 1 over 100 times as intense. Okay? So we can see 4 is smaller than 6, so it's weaker. Okay, how much weaker? 1/100th weaker. Okay? All right. Letter D. An earthquake of magnitude 4.8 is how much as intense as magnitude 6.8? Well, you're going to do the exact same thing as you did on C. You're going to go 4.8 subtract 6.8, and you'll get the exact same answer as C, 10 to the negative 2. 10 to the negative 2, again, it's going to change to 1 over 10 squared, which is 1 over 100. 1/100th. Letter E, it says, the 1960 earthquake in Chile was blank times as intense as the 1976 earthquake in Italy, and blank times as intense as the 1983 earthquake in Colombia. So first of all, we have to locate all those on our Richter scale here. So we're talking about the Chilean earthquake in 1960. So we got to find that one here, and that's 9.5. Okay, so the Chilean is 9.5. And this 1976 earthquake in Italy is a 6.5 we locate. Okay, so that one's 6.5 on our Richter scale. And the 1983 in Colombia, that is a 5.5. Okay, so the Colombia earthquake in 1983 was 5.5 on the Richter scale. So we're going to compare all three of them. So what we're going to do to the first one is we're going to say, okay, we're comparing the Chilean to the Italian one. So we're going to take, and we're going to go 9.5, well, 10 to the 9.5, subtract 6.5. How big is that going to become? 10 exponent 3. Well, 10 exponent 3 is 1,000. So that means that the earthquake in Chile was 1,000 times more intense than the one in Italy. Now, how much is the Chilean compared to the Colombian? Because you're comparing the Chilean, the first one here, the 9.5, to the Colombian one. You're not comparing Chilean to the Italian, then Italian to the Colombian. You're comparing the Italy one and the Colombia one, both, to the one in Chile. So the next one, we're going to go 10 exponent 9.5, subtract our 5.5. Well, that's going to give us 10 exponent what? 4. Good. So it's 10,000 times as intense. It's 10,000 times as intense. Now we're going to take a look at the one in Turkey. 1966, the earthquake in Turkey was blank times as intense as the one in Japan in 1933. So let's locate those ones. Japan 1933 is 8.9, and we have Turkey 1966 is 6.9. Now who comes first? Who are they comparing to who? They're comparing Turkey to Japan. I'm going to put 6.9 first. So you've got 10 to the 6.9, subtract 8.9. Whoops. So what's that going to give us? 10 to the negative 2. Good. So F is going to give us 10 to the negative 2, which, like over here, we're going to flip it, and it becomes 1 over 10 squared to give us 1/100th times as intense. Okay? So in other words, it's weaker. By how much? 1/100th. Okay? So whenever you're talking about the intensity, you're talking about how strong the earthquake is. Okay? Good to go so far? All right. Well, let's move on to the next section. Okay. Now the Richter scale gives us a really big equation where it says magnitude 1 subtract magnitude 2 is equal to log intensity 1 divided by intensity 2. Well, we know that we can change our intensities 1 divided by 2. If we get rid of the log, how do we get rid of log? What is the base on log if it's hiding? 10. So if we base 10 that, the logs disappear, and we got to base 10 the magnitudes. That's where this equation comes from. Okay? The one that you ever need to worry about is the one with the 10. Okay? The ones we just did. Okay? Intensity 1 divided by intensity 2. And why is it dividing? You're comparing them for intensities to see who's stronger. Now, why am I subtracting when I'm dividing? Because they're exponents, exactly. Okay, those exponents for the magnitude, okay, they're magnitude exponents. And if they're exponents, you need to subtract them when you divide. That's where this whole thing comes from, subtracting the magnitudes, okay? The exact same thing we just did. Let's take a look at this first one. And they're always going to kind of show it to you like this. But really, all you need to remember is this part of it, where you take 10, magnitude 1, subtract magnitude 2, whoever you're comparing. Okay? All right, let's take a look now. It says, how many times more intense was the 1960 earthquake in Chile? It's telling us it's got a magnitude 9.5 than the Chilean at 7.8. All right, and what's the answer to the nearest whole number? So the way we find that, we're going to say intensity is equal to 10 to 9.5 subtract 7.8. So what's our intensity going to become? You're going to get 1.7. So it's 10 to the 1.7. Now you actually have to solve 10 to the 1.7. Everybody solve that, please. Type in 10 exponent 1.7. You should get 50.1187 and so on. It's a run-on decimal. So one of your nearest whole number, it's 50 times as intense. So our intensity is 50. Okay, so it's 50 times as intense. Or you could say it's 50 times stronger. A lot of people like to use the words stronger and weaker, and that's just fine. Okay, here's a few more for us to take a look at. Now, number 2 says, how many times stronger in terms of energy is a magnitude 6.8 than a one which is 6.0? So how many times stronger is it? Well, you're going to take the big, subtract the small. So it's 10 exponent 6.8 subtract 6.0. And you're going to get 10 exponent 0.8. Type that sucker in and see what you get. You're going to get 6.3095 and so on. So it's going to round to 6 times. Okay, so it's 6 times stronger. You could use, again, the word as intense if you like. Okay, let's try 3. How many times stronger is a 5.1 than a 4.9? You guys do that one? Push pause now and play when you're ready. Okay, taking a look at number 3. We should have set it up this way. 10 exponent 5.1 subtract 4.9 to give us 10 exponent 0.2. Well, that's going to give you 1.5848 and etc., which rounds to 1.6. So it's going to be a 1.6 times stronger. Okay? Now, number 4 is a bit different, because number 4 isn't telling us how big the minor earthquake was, but it's telling us that the big earthquake was 375 times stronger than the minor one. So we're going to actually have to find out what the magnitude of the minor one is. So there's a couple things we have to know. Logically, we have to understand if there is a number that is a whole number. If it's a whole number, it means it's stronger. If it's a fraction, it means it's weaker. So for example, remember when we did those questions at the very beginning where we had 10 to the 9 subtract 8, you get 10 to the 1. Okay, so that's going to give you 10, which is a positive number, and it's a whole number. Okay, it's not a fraction. But when you did the other questions where you got 10 to the negative 2, you got 1 over 100. If you get a fraction, that means it's a weaker earthquake, which means it's going to be a smaller earthquake. Okay, so if they're telling you the earthquake has a whole number intensity, that means it's a strong earthquake. And if it's comparing it to a different earthquake, and it says it's a fraction of intensity, that means that the one you're comparing is smaller, and the other one you're comparing to is the bigger one. Okay? So we're given 375. So we know that the 7.5 earthquake is the bigger earthquake. We know that the other one is the smaller one. Okay? So we're going to set it up. So how do we know? A is just saying, is the minor one going to be bigger or smaller than 7.5? It's got to be smaller because 375 is a whole number. Okay? It's not a fraction. So we're dealing with a smaller earthquake. We're going to try and figure him out. So we need to set the equation up. We're now going to have to solve this guy. We're going to be solving for x. So now we set it up this way. 375 is my intensity. I have my base 10 for my magnitudes. My big magnitude was 7.5. Do I know my minor earthquake? No, that's what I'm looking for. So we're going to subtract x. So now we need to solve for that. Now, why is it called the log scale? Because we have to log both sides now. Okay? Now, what do we know if we log a base 10? If I go log 10 of 10, and I have an exponent up here, so these are going to cancel, aren't they? And my exponent comes down. That's the whole point of us doing this and logging both sides. Okay? So, let's log both sides and see what we get. So, I'm going to write log of 375 equals log base 10 of 10 to the 7.5 minus x. Our base 10 and our log disappear. So I have 7.5 subtract x equals my log 375. I just switched them places left to right. Am I able to do that? Yes. Okay, there's an equal sign. You can switch things side to side if you switch the whole left and the whole right. Okay? Now we need to get rid of that 7.5. How do I get rid of a positive 7.5? We're going to subtract it. So we're going to subtract 7.5 to both sides. So we're going to subtract 7.5. Now, since I'm subtracting 7.5, we're actually going to put that out front of log. We're not going to write it after log. Because if we do write it after log, it's going to be sometimes confused with the 375. Some people think that you have to take the 375 and subtract the 7.5. That's not correct. So we're going to subtract 7.5 in front of log. Okay, but remember, log is a plus, so it's going to connect to it with a plus sign. So I'm going to get negative x equals negative 7.5 plus log 375. Okay, so that's what it's going to look like. Now, can I ever solve for a negative x? No. So what's my last step here? What number's hidden in front of him? Negative 1. So what do you have to divide by? Negative 1. You divide everything by negative 1. And I'll show you the quick trick to this in a moment. So we're going to end up with x equals 7.5 minus log 375. Let's take a look at those signs now. Why did they change? Because you've got a negative dividing by a negative to give you a positive 7.5, and you've got a positive log dividing by a negative to give you a negative log. Okay? That's why it ends up that way. What do you notice about this equation, the way it's written, and the way this one is written? What do you notice about those? Who switched places? The x and the log 375. All that happened was x and log 375 traded places. Does that make sense? Okay, that's the quick trick when you come to this type of question. Okay, so whenever you get a digit subtract x equaling the log, just switch the x and the log places. Okay, and then you don't have to do this divide by negative 1 stuff and then change things around. Okay, that's the quick trick, because we're just going to end up with this. So everybody in your calculators, type that in. Go 7.5, subtract, log 375, enter. And remember, we're looking for a magnitude of an earthquake, so you're going to round to 1 decimal place. Okay, we should have got x equals 4.925, etc. So the 9 doesn't round up. Our earthquake was a 4.9 magnitude. Okay, now you can check your answer. You can go 10 exponents, and you can take your exponents, subtract them. You can take 7.5, subtract 4.9, subtract them, and then go 10 exponent that. You're going to get an answer that will round to 375. That's how you check your answer. Okay? Now we're talking about the pH scale. You deal with the pH scale a lot in chemistry. Now you're going to deal with this equation a lot, where you say pH is equal to a negative log of the hydrogen ions. H plus is hydrogen ions. And that's always in moles per liter, which I'm sure you're used to seeing. So, you guys have had a chance to read through that. Here's our pH scale. As you go further left on the scale here, you get more acidic. As you go further right, you get more basic. So as the numbers increase, the acidity reduces and it gets more basic. Okay? Basic, another word for that is called alkaline. Okay? Now, let's take a look at how that works for us. We do the exact same type of thing. If they don't tell us the moles per liter, we can find it out if they've given us both of our pHs. Now, we can also find pH if we're given moles per liter and the other pH. So let's see what it's going to look like. We're going to compare on this chart. We've got tomato juice. So let's find tomato juice. Tomato juice is a pH of 4. So if it's a pH of 4, is it acidic or is it basic? It's acidic. You bet it is. Okay, and then we want how many times acidic is it as pure water? Well, let's look at pure water. Now, when we compare this way, we need to compare it. Are we going to take 4 subtract 7 or 7 subtract 4? They're exactly opposite. 7 subtract 4. Okay, 7 subtract 4. Now, why? Because it's saying how many times more acidic is it? Okay, we're asking how much more acidic it is. If it said how much is the alkalinity compared to pure water, you would take 4 subtract 7. Okay, so it depends on which way you're moving down the line. Okay, so that's going to give us 10 exponent 3, which is going to give us 1,000 times. So tomato juice is 1,000 times more acidic than pure water. Okay? Now let's do the same thing with eggs. Eggs is how much times as alkalinic, so it's as alkaline as pure water. So we want eggs and pure water. So now we have eggs 8 and pure water 7. So we're going to take 8 subtract 7. How come? Because we're comparing the alkalinity. So 8 subtract 7 is 1. So it's 10 times as alkalinic as pure water, meaning it's more basic, it's more alkaline. Okay? And we know that just by looking at the chart. Pure water has a 7, and which one was it? Eggs have an 8. Okay? The next one again, we have eggs, which is an 8. And we want how much acidic is it as pure water? Well, now we're comparing to the acidity. We know that it's more basic, so now we want to take the lower number to compare acidity. So now we're going to go 7 subtract 8. So now we're comparing the acidity. Who's more acidic? And how much more acidic? Well, we're going to say eggs are 10 to the negative 1, which is 1/10 as acidic as pure water. Okay? Which means it's weaker. It's not as acidic as water. We know that already because it's more alkaline. It's got a higher pH. Okay? Which means it's not as acidic. Milk of magnesia is 1,000 times as what as blood? Are we going to say it's as 1,000 times as acidic or alkaline as blood? Let's take a look at what the numbers we're comparing is. We want milk of magnesia is a 10.5, and we've got blood, who's a 7.5. If we wanted to have 1,000 times, we know that they took 10.5 subtracting 7.5. That's what they had to do to get 10 to the 3. Okay, that's how they got 10 to the 3 for the 1,000 times. So is it going to be 1,000 times what? Alkaline, good. Which means it's more alkaline than blood. Okay, so it's more alkaline. That's why when you're having an upset stomach sometimes, you use the milk of magnesia and you chunk some of that stuff. Another word is, that's also called Pepto-Bismol. Okay, so chunk some Pepto and it coats your tummy. Okay, which coats the acids. It makes your stomach less acidic and more basic. Does that make sense? That's why it works. Okay, now it's saying something is 100 times as acidic as normal rain. Okay, which means it's more acidic than normal rain. That means you had to take something and get an answer of 10 to the 2. So you had something subtract something equals 10 to the 2. Because 10 to the 2 gives us 100. So now we're comparing something to normal rain. Let's find normal rain. Normal rain's a 5. So is the 5 going to go, where's the 5 going to go? What are you going to do? It's going to be the first one. And what are you going to put next? The vinegar. Good. 5 subtract 3, so it's vinegar. Vinegar. Okay, vinegar. So vinegar is 10 squared, so 100 times more acidic than normal rain. Okay? So they call it acid rain. You know the acid rain we get? Okay? All right. Eggs are 1/10,000 as alkaline, which means it's not as alkaline. It's weaker alkalinic, which means it's more acidic. Does that make sense? If it's got this kind of an alkalinity, it's more acidic. Okay, does that make sense? Okay, so let's take a look at that. You're going to put something, subtract something. So you want something that's going to give you a 10 to the negative 4, right? That's what we're looking at, 10 to the negative 4. So eggs. Eggs are 8. So where's the 8 going to go, first or second? It's going to go first because you're comparing alkalinity. Okay? So which one is 4 times bigger than the 8? The 12. If you take 8 subtract 12, you get negative 4. So eggs are more acidic, basically, than washing soda.
No.
Yes. Washing soda. Okay? All right, let's take a look at the next question. Okay, got a couple minutes to look at these ones. So pure water is 7, swimming pool is 7.5, and seawater is 8.4. We're comparing alkalinity. So it doesn't tell us how much more alkaline or less alkaline it is. So when we compare alkalinity not knowing that, you start with the largest number subtracting a big number, or sorry, a small number. So seawater is 8.4, so we're going to have 10 to the 8.4, subtracting pure water, which is a 7, to give us 10 to the 1.4, which is going to give us 25 times. Okay, so it's 25 times as alkaline, so 25 times more basic. Okay, take a look at B, seawater. How many times more alkaline? Again, you start with alkalinity, and you don't know how much more, so you start with big numbers, subtract small. So 10, 8.4, subtract 7.5. This time, we get 10 exponent 0.9, which is going to give us 8 times roughly. Okay, check your work. Now this is a lovely question. A patient gave a urine sample, which was found to have a pH of 5.7. What was the hydrogen ion concentration? All right, now we have to actually use that other equation. So our equation is, where are we here? pH equals negative log of the hydrogen ions. That's the equation we're actually using. So we plug in the numbers we have. Okay? So the number we have is our pH. We don't know the hydrogen ions. We're going to figure that sucker out. So this is going to look like this. 5.7 equals negative log hydrogen ions. Okay? Now, the first thing you have to do is divide out that negative 1 in front of log. You're going to divide it out to both sides. So basically, your pH is going to become the negative on the left. Okay? So you're going to get negative 5.7 equals your positive log of the hydrogen ions. Okay? Now, how do we get rid of the word log? Put a base 10 on it. Okay? If you base 10 it, meaning you change the word log with the hydrogen ions to this. You're going to change it to log. Remember the hidden base 10? Well, you're going to put a 10 there, and now the hydrogen ions are going to become the exponent. That's how we're going to get rid of the word log. Equals on the other side. If we base 10 it here, what are we going to do to the other side? Base 10 it. So we're going to have 10 to the exponent negative 5.7. Okay? Now, base 10 and our log disappear. So our hydrogen ions are equal to 10 to the exponent negative 5.7. So that's exactly the answer. You type that in, and we're going to find out what the hydrogen ion concentration is. Okay, and we want moles per liter. So you're going to round to 1 decimal place. So round to 1 decimal place. That's how moles per liter are rounded. So type in 10 exponent negative 5.7. You're going to get something E negative something, correct? Yes, you get a decimal E negative something, and that's what you want. So you get 2.0 blah, blah, blah to run on times 10 exponent negative what? 6. Good. So your answer is 2.0, you're rounding to 1 decimal place, times 10 to the negative 6, and again it's moles per liter. Okay, so there's your hydrogen ions. That's how you solve that. Okay, so let's write number 2 out. It gives us the hydrogen ions, so that's going to go into the hydrogen ions in our actual equation. So I'm going to have pH equals negative log 3.4 times 10 to the negative 4, and then you hit enter. What are we going to get for a pH? Remember, pH is 1 decimal place, so round to 1 decimal place. 3.5, good. So your pH is 3.5 you should get. Okay, check your work. Okay, last question here on pH. We're given 2 pHs, so all we're going to do is set it up as 10 exponent something subtract something. So 10 exponent something subtracting something. Now I have to find out which numbers are subtracting. So I'm comparing acidity. Okay, if you're comparing acidity, you're going to take a big number, subtract your small number. So you want to find out how many more times acidic it is. So you're going to go 4.1 subtract 2.4 to get 10 exponent 1.7. Now, why do you know you're going from 4.1 minusing 2.4? Because you want to know how much more times acidic the 2.4 is compared to that 4.1. So that 2.4 is more acidic, but how much more acidic? Well, it's 10 to the 1.7 more acidic, which gives us how much? Exactly, 50 times more acidic. Okay, it's 50.1187 again, so you're just going to round it to 50. Okay, decimal scales is talking about how much you can hear and how loud things are. You've had a chance to read this page, and you've had a chance to read this one. So now we're going to take a look at the example on the bottom. So we want to know how many more times intense is the sound of a piano playing than a whisper. So just like the pH scale, and just like our magnitude scale, we're going to be using this one, because we're giving it in decibels. So it's going to be 10 exponent. Now our numbers that we have for our decimals, we need to divide by 10 after we subtract them. So we've got 67 subtracting 22, then we divide those by 10. Okay, so you're going to get 10 exponent 4.5 divided by 10, which is 10 exponent, sorry, 45, not 4.5. 45 over 10, which gives you 10 to the 4.5. Okay, so that's all it is. Do you have to do all of those steps? No, you can go from the first to the last right away if you like. So you're just going to type in 10 exponent 4.5, and that's how many more times louder a piano is than whispering. Okay, so hopefully you got this. It's a big number. 31,622. Then you're going to get decimal 7766. So if we round to one decimal place, okay, you're going to round to one decimal place, you get 31,622.8 times louder. Okay, it's that many times louder the piano is than whispering. Okay? Okay, these three questions. The first one you should have taken, 120 subtracting 80, you're going to get 40. Then you're going to divide by 10 to get 4. So it's 10 exponent 4, which is 10,000 times as intense. So 10,000 times louder. On this one, we're going to take 145, subtract 125 to give us 20. Last step, divide by 10 to give us 10 exponent 2, which is 100 times louder. Then the last one, I'm going to take 30 and subtract 60. And then I'm going to divide it by 10, so that's going to give me a negative 30 divided by 10 is a negative 3. So that's going to give me 10 exponent negative 3, which is 1/1000. Okay, times as intense. So it's a softer sound, it's not as loud. Okay, let's look at the next couple questions. On the bottom of this page, how many times louder is 108 decibel sound than 100? 108 minus 100 is equal to 8. Divided by 10 is 0.8. So you're going to get 10 to the 0.8, which gives us 6.3 times louder. And on the bottom one, 97 subtract 93 is going to give us 4. Divided by 10 gives us 10 to the 0.4, which is 2.5 times louder. Okay, check your work. Okay, exponential growth and decay. We're going to solve some exponential equations using logs, which means they have different bases. We solved the other ones using the same bases, so we could drop the base. We didn't have to use logs. This time, these questions are going to have logs. Whenever you see a list of data, the first thing you're going to do is put it into your lists. If it's a horizontal list, like the first one you see, the top goes into list 1, the bottom goes into list 2. A good hint, if you see bigger numbers for x, that means it's going to have to be a log regression. So you're doing log regressions on those. Push pause now and play when you're ready. Okay, we're going to round each parameter to 3 decimal places. So it is a log regression, which is ln. You should get y equals negative 100.327 plus 11.019 ln x. That should be your equation. Now the question's actually saying, how long is it going to take to double the original value? Well, you started with $9,000, okay? Doubling that would be 18,000. Now remember, 18,000 is an x number here. So to find the y number, if you look on the chart, when you know x and you find y, you do second trace, value. Value is number 1. When that comes up, an x equaling is going to come up. That's where you type in your 18,000 and then hit enter. And that's going to give you what y equals at 18,000. And here y is talking for time. So type that in and find out how big it is. How long is it going to take for it to double to 18,000? And go to the nearest tenth of a year. So the nearest 1 decimal place. The nearest tenth of a year. What did you get from y? You're going to get 7.6. Okay, everybody get 7.6? Okay, check your work. Now there's something we can do. It's called the rule of 72 for doubling money. Now, we can also do the rule of 72 here, everybody. And this is much quicker. Now, we need to always do the regression equations. That's no problem. But we can check our work by doing rule of 72. If you go 72 divided by interest rate, leave the interest as a decimal. Everybody take 72 divided by 9.5. See what you get. 7.6. Imagine that. So the rule of 72 works, but only if it's compounded annual. So this is compounded annual, so the rule of 72 works. So if we're taking 72, dividing it by 9.5, you leave it in that, we're going to get 7.6. So 7.57, which rounds to a 6. Okay? All right. Let's take a look at number 2. Number 2, you also see a list of data, so put those in your list and do a regression on that one. Okay, on this question, again, you're going to put these guys into list 1, list 2, do a ln regression, number 9. So you're going to find an equation that looks like this. Y equals negative 179.6 plus 18.679 ln x. Okay, now doubling your money, you could have did 72 divided by 5.5, the rule 72, because it's compounded annually, so that'll work. So that's going to give you 13.09. Now, if we do it algebra with the calculator, you're going to go second trace, value of x, and type in 30,000, because 30,000 is the doubling of 15,000. How long does it take you? You're going to get 12.94. So 13 years. 12.94 is what you get. Okay, so roughly 13 years. Let's take a look at the last 3 examples here. Base E. We solve them the same way, only instead of logging both sides, we're going to ln both sides. So let's see how it works. So we've got our base equation here. I equals IO E exponent negative K times T. Now what's that talking about? Well, it says the current amps, the current amount is IO. Your current amps for electricity fall to I amps. Okay, so that's the second. So they start at IO, that's always your starting, your initial, and they end at I. Okay? And it's saying after how many seconds? T is how many seconds? Now we want to know the value of K. We have, if a 25 amp falls to 2.5, so we're going to plug our numbers in where they go. So 2.5 is I, 25 is IO. So our equation is going to look like this. 2.5 equals 25 e to the negative k times, how many seconds does it happen in? 0.01 seconds. So t is 0.01. Okay, that's what your equation looks like to begin with. And we're just plugging numbers in that match. Okay, that matches that, and the t matches that. Okay? Once we've got those done, How do we get rid of the 25? We have to divide it out. Why can we divide the 25 out? Because it doesn't have an exponent, neither does the guy on the left. Okay, if the guy on the left had an exponent, we couldn't divide it out. So we're going to divide both sides by 25 first. We're going to get 0.1 equals e exponent negative 0.01 k. Okay, because negative k times 0.01 is negative 0.01 k. We've just multiplied that into the bracket. Now that we're back to this stage, how do I get rid of an e? The same way you get rid of a base 10 is you log it. But this time we're not going to write log on both sides, we're going to write ln, ln. Okay? So we're going to ln 0.1, and we're going to do ln, which is base e. You don't have to show the e because it's hiding, to the negative 0.01 k. With this, base e and ln, they disappear. So now we get negative 0.01 k is equal to ln 0.1. Okay? I just switched them sides. You have an equal sign. It's okay to do that, as long as you take everything from the left and switch it with everything on the right. At this point, the last step, divide by what's sitting beside k to both sides to solve for k. Okay, solve for k and round to the nearest whole. It's asking us in the question to round to the nearest whole number. Okay, our last step to isolate k is to divide by what's sitting in front of them. So you divide both sides by negative 0.01, and we're going to get k is equal to 230. How come? Because you get 230.25, and it wants the nearest whole number. So it's going to be 230. Okay? Okay, last two questions are both finding the error. So we have a shoe store. Rebecca solved the equation, which is this. Okay, this is the equation. She solved that equation. Now, where did she come up with that equation? Well, first of all, we have to read what it's talking about. So Sharon's Shoe Store is having a closing down sale. During the first week, prices are reduced by 12.5%. So we're going to use this equation that does this. Y equals A1 minus I to the n, right? We have to use that, 1 minus. So let's see what happens. Y equals. Now, where is the 100 coming from? Let's take a look. It says, students were asked to determine which week the sale of a pair of shoes originally starts at $100. So that's my A, my starting amount there, or actually it's P. So my starting amount is $100 for this pair of shoes. Okay? Then it says it's going to be advertised at sale for half price or less. Well, what's half of 100? 50. Well, that goes where our Y is. Okay? Now we need to put our decimal into our percent into a decimal. So you go 12.5 divided by 100 to give you 0.125. Now, we can't take and just put 0.125 in there because we're reducing by that much, which means we take a whole and subtract the 0.125 exponent n. So that's going to look like 50 equals 100, and now we're going to do the subtracting. 1 subtract 0.25 gives us 0.875, all exponent n. So let's check her work. Let's see what she did. That's the equation we should be looking at. She got this equation. What's wrong with her equation? She didn't subtract from 1. Exactly. So she made a mistake in line 1 when she set the equation up. Her decimal in the bracket is wrong. So she made her mistake on line 1. Let's solve it completely now from this point and see what the actual sale, or what week the sale price is going to be, half or less. Okay, solve that equation. Push pause now and play when you're ready. Okay, let's take a look at what you've done. First thing is you're going to divide both sides by 100. Then you log both sides, right? Log in front of both. After that, you need to take the n out of the exponent and bring it down in front of log. At this point, now you're just going to divide both sides by what's sitting beside n. So you're going to divide both sides by log 0.875. Okay, you're going to get n equals 5.19, so 5.2. So after week 5, it's going to drop to half price. So in week 6, it'll definitely be half price or less. Okay, so the nearest week, we're not going to say week 5, because at week 5, it's not half price or less. We have to round to the nearest week. And in this case, we actually round up even though it's only 0.2. So the nearest week will be week 6. So if that was a multiple choice question, and it was only whole numbers, 5 or 6, you would have to choose 6. Because at week 5, it doesn't get to half price or less. At week 5.2, so it's halfway almost into week 5 before it gets to half price. So that means by week 6, it'll definitely be half price or less. Okay, so our answer to that one is week 6. Okay, last question. There's an error in this one as well. Try and find the error and then fix the error. Last question. Push pause now and play when you're ready. So the error in this question, hopefully, obviously, you noticed it was line A. In line A, they did not put brackets around the exponents when they put them out front of log. That is necessary because it's a binomial, meaning there's more than one term as an exponent. If there's more than one term, it has to go in brackets. If not, you'll make an error like what happened here. You cannot move that 3x over to the 4x yet. You have to split the logs. So what we're going to do here from line A, we split the left side. So we're going to have 4x log 5 subtracting 2 log 5. So the 4x and the negative 2 each get log 5. Okay, it splits. And you'll have to do the exact same thing to the right-hand side. So the right-hand side will be 3x log 3 plus 2 log 3. Okay, so that's what you're going to get for the right-hand side. From that point, let's solve these. So I'm going to have one equaling the other. Okay? At this point, you're going to bring the 3x log 3 to the left. You're going to take the guy without x to the right, so the negative 2 log 5 to the right. Okay? This is back from lesson 3 and 4. So we're going to get 4x log 5, who originates on the left. If he starts on the left, he has to be written first on the left. Then our positive 3x turns to a negative 3x log 3 on the left. Okay, there's our left-hand side. The right-hand side, 2 log 3 originates on the right-hand side, so it has to start on the right-hand side. So 2 log 3. Now you're bringing over the minus 2 log 5, so the minus 2 becomes a plus, so plus 2 log 5 is written after what originates on that side. Now we have our equation proper. The last thing we have to do is divide x out on the left, divide x out, and basically you just rewrite the left side without x sitting beside them. So we're just going to have 4 log 5, subtract 3 log 3. Okay, you take the x out from sitting in between them. Okay, no more x. On the right-hand side, the right-hand side stays the same. 2 log 3 plus 2 log 5. Last step, divide both sides by what's sitting beside x. So we're going to divide both sides by 4 log 5 minus 3 log 3. And there's 2 things. It has to be in brackets. 4 log 5 minus 3 log 3. Okay? Solve that to the nearest 2 decimal places, please. Okay, rounding to 2 decimal places, you should got 1.72. Okay, check your work. This concludes lesson 1.6, log scales.